Bootstrap first. We're going to talk about model selection methodology. Then we're going to go back to.
Oh, is this a whole new swag?
This is chapter 6. I can, if you guys want to grab chapter 6, just grab chapter 6 off of the Stat Learning website. It'll be the same as what we're doing if you need it. Do you know where it is?
Mm-hmm. I just usually.
Let me show you.
I have the book pre-downloaded.
Okay, on Stat Learning, you go to Resources, Second Edition. Underneath Slides, you have all the chapter slides.
Okay.
I would log into Canvas, and I actually could probably do it. Try to do it from my phone while I'm talking. It just takes so long to do it, because I have to log in, verify, and all the other stuff.
That's fine. I'll get it. Now that I know where to go on the website, I can get it.
I thought about how I was going to do this, and you're a 03486, right?
Yes.
Yep.
Better be 486 or I'm in the wrong class. And I haven't been for over half a semester.
Well, I just love how long it took for the put your class number up there, because I thought you were being section. I'm like, shit, I don't know the section. I know the class number. That was fun.
Are you sure you're allowed to be here?
No, the government told me I'm required to be here, so yes.
Allowing required too.
No, let's not do that. That's cooking my brain. All right, so yeah, once again, linear models, yay. This is boring. Praise of linear models, great interpretability, relatively good predictive performance. Okay. Relative predictional accuracy. For a situation whenever p relative to n, you're likely to get a spatial predicted accuracy characteristic with respect for systematic design. So what we say here is that linear models have one relatively interesting aspect to them that make them good at working with situations where individual features, P, predictors, can be characterized for low numbers, low n, right? So we talked about the idea of utilizing linearized thresholds or linearized reconstruction systems, but we're going to talk about something called least squares methodologies as an alternative to strictly picking which of the linear selection elements that we work with. If you recall, we had the forward linear and backwards linear selection for feature inclusion. Instead of utilizing that methodology, what we're going to do to pick the characteristics or key features from the system and determine their relative coefficients for the system, we generalize from the strict linear models out into accommodations of nonlinear and additive relationships as well. All right, so this is where you can effectively model one region of a specific larger, more complex function, create smaller little chunks of models, and then tell the system where which model is used in the space. So we needed to solve the whole problem, right? But we originally started off with the neighborhood approach. What generalized additive models actually do is they take advantage of the combination between those, right? I can establish the neighborhood within which to apply the model characteristics for that space. But we're also going to talk about the idea of which of these dimensions, which of these predictors P, are the ones that actually make the best case for describing what's going on either throughout the entirety of the system or within a local space. So we're going to look at two methodologies for it, and then we're going to go back to the Bootstrap because I think Bootstrap makes a little bit more sense with regard to some of the mathematics once we go through some of this stuff. All right, so we said previously that while linearized models operate with distinct advantage in interpretability, they are limited in their capacity to describe certain relationships. So we were going to talk about a methodology for, as I said, relationship-wise, for replacing this using the least squares fit or ordinary least squares fit system. And our core goal here is to maximize, as I said previously, this prediction accuracy capacity and model interpretability by deriving a method for that feature selection process. All right, so we've already talked about subset selection. We're going to go through it again, and the subset selection will allow us to be able to describe something that we know intuitively, right? We know intuitively that there are certain things about an object or individual that, as those parameters are adjusted or exchanged or balanced, will affect our capacity to see what it can do in the future. Its interpretation of its parametrics, only some of those matter, right? Only certain things actually make a difference with regard to whether or not this thing is going to work. It doesn't matter whether a ball is blue or purple with regard to how high it'll bounce when you throw it, right? That is where you look at it and say, okay, that's an unnecessary element, it's an unnecessary feature. So we're going to say, within this framework, we have an identification framework of P predictors, and we believe that some of them are related to the response, but not all of them. Or at least we'll say that there is a unique subset which is most highly correlated to those responses when we fit the model utilizing our least squares methodology. We're then going to talk about shrinkage methods, which involve modifications of utilizing all P predictors with estimations of the coefficients shrunk towards zero. This one's weird. We're going to talk about two ways in which this process works. And we're going to talk about two methodologies. Shrinkage methods are actually also known as regularization. Right? So regularize a model is to shrink its coefficients. Regularization follows two methodologies, that is ridge regression and what is called least absolute sum of squares operative, or lasso methodology. It doesn't have anything to do with lasso, however, it does have to do with the lasso selection tool. If you've ever played with one in like Photoshop or Paint or whatever, you know, you get the little lasso and it's got the thing where you can sort of drag around the part you want. It's very similar to that, right? The lasso methodology allows us to focus in on a specific subset of regions in a non-linear way. We don't have to take them on, adding them one at a time. And then we'll talk about dimensionality reduction methodology, and this is what's going to allow us to be able to understand a little bit more, and we're going to do this in conjunction with the bootstrap methodology. We're going to talk about this together with bootstrap, yes.
Does that help kind of overcome the curse of dimensionality in some of the modeling?
Absolutely.
Okay.
Yes, that is in fact the state. The weird part about dimensionality reduction is in comparison to these other methodologies, it leverages something that's similar to the linear discriminant methodology that does not need to be informed by the labels, right? So when we talk about dimensionality reduction, we're going to talk about our first regularly used unsupervised method, right? So with the principal component analysis is what we're going to focus on in that space, which is also called singular value decomposition, or SVD. SVD is a slightly different version of it, but it's similar. But we're going to focus on principal component. And the cool part about principal component is I don't actually need to know the labels of the data, so I can utilize the whole data set to establish the optimal projections for those patterns. I can start off in 6 dimensions and end up in 3, and the 3 that I keep are actually informed by all 6 original dimensions. I keep things from each dimension, and I create 3 new predictors that are in fact a linear recombination of those original features. So now it's 3 dimensions reduced in terms of as you say, Chris, dimensionality, but retaining the maximum amount of information from those 6 dimensions as an independent decomposition. Okay, some of this stuff gets a little heady. I do admit that the last sort of the second half of the class is going to get more intense, but what I actually expect you to know of it is going to be more anecdotal, incidental, key features, high-level points. All right, so this slide is probably a pretty good place to sort of look if you're interested in like review later on. I'll give you a high-level overview of a lot of the things that I think are important. But as far as the terminologies themselves that apply to these things, you'll have to go and pick those out from the subsequent slides. Okay, subset selection. We talked about best subset selection. Matter of fact, I actually had an exam or question on your exam about best subset. You might not have known it was there, but it was there. All right, because I said guaranteed best subset with regard to forward selection, and the answer to that is no. There's no way you can guarantee to get the best subset whenever you're using either forward or backward selection. The reason why is you have to do what in order to make sure you have the best? You have to check all of them. And any sequential model is not going to be capable of checking all of them. So we denote the characteristic first being the null model. We'll call that model M naught. That's the first model characteristic. That is that there is no relationship to the predictor output. So no predictors are contained within that model. Effectively, the only characteristic that's contained within that model is based upon the mean of the distribution of the targets. The reason why I say that is because beta naught, our bias term or intercept, y-intercept, is established based upon the mean of the distribution for the targets. I will then continue adding a single feature k to that system and keep restructuring for p subsets, right? So k elements, so it is new p subsets, p primes, effectively created of k of p. So I start off with 1 of p. What do we end up with? We end up with p models, right? Then we end up with 2 of p, right? We end up with 2 of k of 2 for p. So let's say p is 10, right? This is 10 pick 2. What does that start to look like? It starts to look like a combination approach, right? So if you utilize strict characteristics of combinatorics, it is the combinations of pick k for the entirety of the set. Now when p gets pretty large and k gets pretty large, the number of combinations that can occur within that space gets crazy, nasty, huge, right? Tens of thousands can occur quickly, where every time you increase one singular number, you end up with thousands to tens of thousands more. The interesting part about it is that it's right toward the middle, right? Right toward where k gets about half p is where you have approximately the highest number of possible combinations through the system, effectively rolling 1 in and 1 out for the whole system. Then as you get further along, where you're starting to get closer to the full number of p, there's actually less total combinations that can play in because you can only roll 1 or 2 items in. So it's kind of this weird curve of the total number of combinations that can occur relative to the size of k. Biggest reason why I'm talking to you about this is computational complexity. The best fit is not functional past a reasonably small number for p. About 7 to 8-ish features is about common for the top end if this has really worked. You get up into 10, you say it's going to take tens of thousands to really create a full comprehensive perspective of all the subcoms that you can work with. All right, so for k up until about 10, for a low numbered p is going to be still a big number. We utilize a variety of metrics, but mostly here we're going to work with best fit being defined as having the smallest residual sum of squares, or equivalency reflective of the largest R square, which is the percentage or the proportion of the variance of that subset captured by the regressive model.
So the P is the numbers of the predictors, right?
Correct.
And K is the class?
No, K is not class here. K is just the total number that I'm choosing to exclude in the subset.
Okay.
Yeah, I know I get you. So if you see C of K, that's class.
Okay, see,
If
okay.
it's C of K, that's class. K is just the iterator. K
Okay.
is just the iterator here. Oftentimes I wish they would use like I or some kind of like common iterator.
J or something, anything.
The I and J are already reserved
I know for
For
the
neural networks.
matrix.
for neural networks.
Oh,
Yeah.
specifically.
Within this space, specifically neural networks, IJ is a common subnotation. So sub X sub I sub J is a common notation for neural networks, or X sub IJ. You know what I'm talking about.
So K is the total number of predictors, right?
Say again?
K is the total number of predictors.
K is the number of predictors at that relative iteration, all right? So if you look at this formulation, we're gonna say that the model will now be conducted. The original model is conducted for M naught. And then the first model, M sub 1, is gonna be constructed from one element of P elements. So let's say there are 10 predictors. I'm gonna say 10 pick 1. I'm gonna end up with 10 models that are gonna be variants of M1, okay?
Okay.
That means that it has a K or size of 1. That is the candidate set. So the candidate set would be, one set has all P in it, right? That's the base set, that's the one we start with. We start off with saying, well, maybe only one feature matters out of those 10. So we're now gonna create 10 different sets, right? It's treating each set as only one individual predictor from that framework. Then we'll start going up to pairs, right? It'll be 1 and 2, 1 and 3, 1 and 4, 1 and 5, right? 1 and 6, 1 and 7, etc. And then 2 and 3 and 4, 5, etc. Okay? So counting the whole thing, factorial, from each of the origins up to the max number. So that's where you use that combinatoric factor of C of P pick K, and you're going to run through the whole system. There's a reason why I say it gets really big number by the end, because you're integrating, every time you integrate up to P, you've done all the integrations for pairs, triplets, quadrats, etc., all the way up to the value of P max,
P max, okay.
right? So P, what you're actually going to do is you're going to do slightly less than P, one less than P. You're never going to do P again, because you've already done it. Okay, you already have that effectively, or at least you should. So, but you're going to compare that. You're going to say, M, the final M version of it is going to be some M of roughly P minus 1 predictors. So it's going to be just a shortened version of the subset. We'll call all the models M sub K's for the relative degree of collection, or the scale of which they capture the original data variance P. And we're going to then reflect that utilizing the largest or maximization of R squared. As I said beforehand, it is the R squared best defined as the variance captured by the model. So we can also categorize M naught to M of P utilizing cross-validation models, right? Remember cross-validation being able to be used for different versions of the subset. What we're going to cross-validate for is, instead of the prediction capacity of a higher dimensionality model, right, of a more flexible model, what we're going to be doing is we're going to be characterizing from null up to P in terms of model system. So instead of model complexity as flexibility across the bottom axis of the cross-validation, it's actually going to be the amount of predictors that we're including. How large is the system going to get? So we'll leave them fixed at low flexibility, and then maybe even change them to slightly higher flexibility to reflect the change in predictive accuracy as the model includes more and more predictors, right? More and more features, more and more information about the data should theoretically produce a higher performing model. But guess what happens? The same thing happens as happens within the complexity increase of a more flexible model. There's a diminishing return, right? You add models, you'll start adding up to P, and you'll get to some point where keeping adding more features will make the model more complex and make it slightly more flexible. Thus what? diminishing return, characteristic divergence, and moving into the memorization area. All right, so we're going to use methods, cross-validation methodologies for the CP criterion. You see C here? You see C here?
Yeah.
This C of P, or what is called the AIC criterion, this is also not a classification.
Okay.
Why? The CP criteria, this is P predictors. So it is the C of P. It is the quality of P. So we say it's a criterion predictor. I'll often just call this AIC. AIC, BIC. This one's also called Malo's criterion, so I'll use Malo's occasionally for you guys. I just try to use the terms that I know, their names, that way if you ever see it in the future. Realistically, here's my goal for this class, and I don't know if I've ever told you guys this. My goal for this class is that if I say it enough times, it'll be in your head in such a way that you go, oh, I heard that once. And you'll know it's a thing, and then you'll be able to look it up later. That's really all I expect you guys to get out of this. It's how it worked for me, okay?
Well, you're doing good so far.
Okay, sweet, that's all you got out of it? So they can say that I've hit that mark.
Well, I think
Thanks,
so. I mean,
thanks.
it's.
We're moving on.
That's the goal for my whole degree.
It's really a pretty good goal, to be honest. Sometimes just knowing what does exist is enough to be able to help you figure out what could be possible to help you solve it.
I actually like the repetition though. It helps me.
Yeah, this
Keep
class
it.
has a lot of repetition in it, unfortunately. Bayes information criterion, that BIC is Bayesian, okay? An interesting course of that is it is a Bayesian inference. We'll talk about these in just a couple minutes, but so let's talk here about predictor capacity. Remember the credit card data. We have actually a lot more predictors than we ever considered within the framework of the data points we were given, right? So you could have stuff like the payment latency, right? What's the duration of the average time between when a statement is issued and when somebody pays it back, right? You could have the frequency of paying minimum balances. That's another consideration. How often is the person paying only what they have to? Total amount of interest accrued is another one that's a metric for determination for potential default. So many of those factors have much smaller correlates to the capacity to truly predict default, but it's still there, right? But incorporation with other things, as we said previously, what's the first feature that's likely to cause us to have the best, the first major drop that's going to happen there? That might be the student predictor, right? Predictor one, number one, best, drum roll please, best possible predictor, we said what was what? How much you owe, right? Hit that $1,500 mark and your default goes way up, all right? So your decidability is going to come from that very first feature. So the reason why this number isn't actually higher with respect to the residual sum of squares is because of the fact that that first predictor contains a lot of the information necessary to make a good quality decision about whether or not someone's going to default. The next three, next three, I guess you'd say, next two or three are going to rapidly, effectively maximize the degree to which adding additional features is going to be productive, right? So by the time we got up to a K of 3 of P, right, we have roughly here, we have something like 11 predictors on this chart, all right? So by the time that I took 3 of those 11, and I picked the max 3, I've effectively maximized the amount of increase that I'm going to get in terms of prediction quality. And I have two things going on over here. I like this particular graph because it shows something that I think I need to start throwing this one in a little earlier in a different way, because I think it characterizes something that's really cool. Notice RSS is decreasing, and notice the curvature. Notice R square increasing, and notice the curvature. They have a slight reciprocity with one another, all right? R square effectively is the remainder total of error that is possible, whereas the residual sum is minimization down to that minimum number, right? Effectively, you will never get up to 1 for R squared, and effectively, you will never get to 0 for RSS. but they tend to move at roughly the same rate with regard to the inclusion of the specific predictor or feature within the system. So as we get here, we say that RSS and R squared are both functional tools that we can utilize to determine whether or not the subset of predictors is useful for us. Now, why did I skip to subset of predictors without going into Bootstrap? Because Bootstrap is a totally different animal. But what does this look like in some senses? You remember we started sequestering samples with k-fold cross-validation, right? What were we sequestering the samples with against them? N, right? The number of predictors. So we put all the sheep off into their folds, right? At that point in time, you were doing whole sheep, whole samples, the whole shebang, whole individuals, classification quantity was put into the group. So effectively, it'd be like taking this half of the class and that half of the class and cutting you guys apart, okay? This methodology is incredibly similar, except for what am I doing now? I'm doing it across the predictors. So what am I doing? You guys remember those things? Well, okay, everybody remembers the blue and red 3D glasses, right? Right, so everybody's, that in 10 years, nobody's gonna know, okay? So it's gonna happen to me. If I stay in this teaching profession, there's gonna be a point in time in which I just don't interface with the students anymore because they're just like, what's a CD, granddad? You know? Like, oh, you mean an MP3? They used to make those on hard disks? But, so 3D glasses, right? Those were the thing when I was a kid. You know, there wasn't, you know, this stereoscopic.
That's how you saw the
stuff.
cool comic books.
Yeah, there were cool comic books. What do they do? What do they do? Both colors are printed on the same page, right? What do those filters do? They don't let that color of light through, right? So you can see the image, the two images superimposed upon one another, slightly shifted off. One comes into one eye, one comes into the other eye. What have I done? I've actually done a sorting process. I've sorted only the things that I'm interested in. So the folding now happens across the sedimentation of information from the individuals, right? Previously, I was sorting you with regard to individuality. Now I'm sorting the power of the features that describe you with respect to a hierarchy of those that are the most important, right? I can take a picture of you in color, and then I can sort out the red, the green, and the blue pixels, and I can try to say which ones of those were most descriptive with respect to being able to identify you guys individually. The answer is green. Why is it green? Anybody know? There are twice as many green pixels as there are red and blue pixels in a camera. So if I sort them into grayscale in any one of those three arrays, I'll get twice as much information in the green because there are twice as many pixels that are taken in from green. That is what's called the Bayer filter. It is red, green, green, blue.
So, can I ask,
Yeah.
out of question, so that's why they use the green screen? Is it for that reason?
Yes, correct. Yeah, it allows them to segment based upon it. Green screen is a little bit more effective than blue screen, but it's also interesting because green is the most common color. It's also the most common receptor in your eye. Also, the other thing that's interesting about it is plants reflect green light, not absorb it. So we actually are able to see things more frequently in the green spectra, but it is not the most effective spectra for the concentration and assumption of energy. So even though it's technically the more prolific band, it's the lower of the power of the bands that the sun puts out.
Okay.
So, sorry, I'm off. I had a professor, all right, I had classes with him in this classroom. His spirit is with us, even though he's still alive. But his spirit is with us here still. His name was Dr. Jerome Knopf. If you guys ever heard of him beforehand, he was a professor here for quite a while. And he used to do this exact same thing where he would go off on totally unrelated parentheticals. And I always just think it's terrible. It's like, how can you do that? Come on, stay on topic. It's like, no, sometimes I think it's actually kind of good to have these little digressions. So we say that subsets are related to the stratification, right, the layering, segmenting of the best portions float to the top, right? So if you sort of put everything in one media and then you float the most effective elements up to the top, you only need the top predictors in order to be able to create a relatively good understanding of what's going on in that space. So here we utilize a methodology for least squares regression, and we say that the deviance is utilized to represent the system here, where we do negative. Deviance is respective of -2 times the maximum log likelihood, and it plays a role of RSS for broader models for classification purposes, right? What are we going to do with this? We'll see in a little bit. So, stepwise selection, we've done this previously, but like I said, I want to keep going with this where I can give you guys the forward model and backwards model quickly. We say that computationally, best subset doesn't work. Why? Any kind of reasonably high number of P, the amount of combinations that you're going to have to explore in order to be able to determine whether it's the best subset is not viable. Too big, all right? So we have to go up with something else. We said that when P is really large, we have to reduce the search space. And whenever we have an enormous search space, you can lead to overfitting and high variance because of the coefficient estimates. This is just a restatement of the curse dimensionality. That's all this is, right? Enormous search space relative to high P. What is that? That's high dimensionality, and says you can have a lot of variance and really, really rough coefficient estimations with respect to their robustness. How well the coefficient is able to predict the output of the system is a characteristic of how precisely the data set describes the phenomena that is being worked with, right? If I only select the features that are necessary to describe what is going on in the space, I need fewer coefficients in order to make the prediction, right? So fewer coefficients means that it is cleaner. It is a more direct dimensional representation of the key search space or the key factors in the system. So if I was making a model of something, let's think about, as again, I use terms from physics because I think physics is a great place to talk about this, because where did we get most of our understanding of models? We looked and observed natural phenomena. First, things like gravitation, etc. And we said, you had Newton sitting under the tree, the apple falls in his head. He then takes a variety of measurements with regard to the concept of gravitation and notices certain patterns within that system. Did every single apple fall at exactly the same rate? No. Aerodynamics, shape changes, eventually the apple will rot and splat, you have to get a different apple. There are things that are going to be inconsistent about the metrics of that system. But at the level of precision that he was able to attain, it really didn't matter too much. So his data was highly variant, right? What's the solution of the high variant characteristic? Get down to where the only thing that you care about is the mass of the apple and the amount of time that it takes to fall a certain distance. Collect enough of that, and all the variance within your individual collections will eventually be flattened out when I remodel. But notice, we don't have a bunch of calculations for gravitation that include wind resistance and characteristics of the object. We just have what? Mass and distance. Those are the only two factors that are calculated within respective gravitation, right? That's all I need to know. I reduced all of the complexity for the calculated sample system, and I said all those other things are so variant with respect to the way they operate that honestly, now that we know that Earth is probably one of the only planets within a relatively long way away here that has anything that approaches an atmosphere, right? Drop something on Mars and wind resistance is so negligible that they didn't think they were going to be able to fly a little quadcopter up there, all right? Despite the fact that its gravitation is so much lower than Earth, they still didn't think there was enough atmosphere in order to fly in a helicopter up there. So what did they do? They looked at it and they said, well, We've got these calculations, these samples, they modeled everything and they did just the basics. They only used 4 characteristics, right? The relative degree of aerodynamics, wind resistance was negligible. So outside of Earth, when we flatten everything, we take the whole scope of all possible gravitation into consideration. Let's say at a planetary level, wind resistance doesn't matter, right? So when we made the generalization for it, what did we do? We reduced it down to only 2 features that we needed in order to make that characterization. That's what this is discussing. That's what the real key to this is. Get rid of everything that is not consistent across all potential implementations for this specific phenomena. And once you understand that those are the only things that are 100% required to make that interpretation or to make that decision about either the classification or the likelihood of the event happening, then you've narrowed it down to the minimum viable product effectively. So stepwise selection is an attempt to narrow it down to the minimum viable product without doing what? Going to every planet in the known universe and checking to make sure that the gravitation works. Okay, we can't do that. So we're going to use stepwise method. Forward stepwise, this is the exhaustive version of it. We talked about it in a very basic way earlier, and I said we would cover it again. N naught denotes null again, right? Obviously, this is non-correlate. And then we start off for incidence. Where do we start off from? K has to equal 0 in this case. The reason why K has to equal 0 in the first case is because that is effectively how we create the null. We create the null by saying it's P pick K, is P pick 0. So the first version of the model contains nothing. Then what's the second version of the model contain? 1 sample. Third version, right? 2 samples or 2 elements. And we're going to go all the way up until we end up with a P minus 1. P minus 1. This is where I say, keep that in mind with regard to forward selection. We're going to then describe M of K for P minus 1 models. Now, which ones are we adding? Which features, which predictors are we adding at each time? When we increase K, how do we pick them? Two 2.2 says, choose the best amongst those, P minus K, for the system. Well, that means we're choosing the best models. But how did we choose which elements, K, of P we selected from to begin with? If I'm only adding 1 feature every time, this is where I talk about that segmentation, or excuse me, sedimentation. The features that have the highest predictive power are going to be the highest scale. You're going to add the very first feature you add when you go from 0 to 1, right? The very first one is going to be within the credit card data as an example, right? That's going to be the amount you owe. The second one's going to be whether you're a student or not. Third one might be if you pay your bill on time, right? Hey, that's pretty good, right? So now I've decided how I'm putting the data features in, right? The next few after that might be something crazy like whether or not you're, married or single, right? That's not a huge correlate because a lot of times married households have as much, overhead with regard to spending, but they also sometimes will have additional incomes. So those 2 features sort of weirdly balance each other out, and it doesn't give a lot of additional information. So it won't be as good of a predictor, but it might have a slight correlation. Then the remainder of the things that are going to happen from there on down are going to be less and less correlated. You want to pick the next best feature along the way. So that's the idea, is that we actually rank the features according to their quality of predictive capacity by utilizing the features that have the best relative RSS when trained on their own, trained in the K of 1 model. So when we start off, we're going to run through, we're going to create a K of 1 model and look at the predictive capacity for the relative smallest RSS for each element as we're picking them to add to the system. What does that cause a problem with? Once again, the same way that we said we couldn't utilize the N of K samples and we created the K-fold methodology to try to not include the test values, because when you utilize the predictive capacity of a feature, you're baking in the decision making. I can't choose a feature based upon its label without including some information about its label into that selection. Just knowing that that feature is a good feature to predict the system, and that it is a good feature over this other feature, is actually informed. It's informed. It learned from that label. That label taught you which one to select it with. So you're biasing the feature selection process by knowing what the label is. So you have to sequester, you have to do this. If you do the process of the forward and backward selection, unlike best set, you have to do your train test split first if you're going to use an information criterion to determine which is the next best feature to add to the system. All right, we do this, as we said beforehand, the same way, and we said the computational advantage over best subset is clear because of the fact that it just does not take near as long, but it's not guaranteed to find a 2 to the p power subset containing p predictors. Thus, the efficacy of forward feature selection is much lower in finding weak covariant additions. We can utilize other methods like ADS-C and ANOVAs to be able to give us those outputs to be able to help with balanced prediction, but we're actually going to use these for limited smaller subsets, all right? We're talking about backward selection. This is one of those things where I say, now that I go through it, you're gonna go, oh, yeah, that's obvious. So backward selection is just the same set as forward selection, but instead of iterating from 0, where do we iterate from? We iterate from p, right? So we start off with the full number of predictors, and then we are going to remove 1, and then we're going to remove it all the way down to just one feature. Now, why don't we go to 0 on backward selection? I have no idea. But the argument here is that there really doesn't need to be one. I don't know why null hypothesis doesn't supply to the backward selection, but I guess the idea is that you can assume that if you're gradually converging to only one singular feature out of a subset, you've eventually gotten down to the minimum level of predictive accuracy. Theoretically, I think this could keep going down to 0 if you wanted to include that M0, that null hypothesis model at the end of the system. So this would be an M of P minus 1, M of P minus 2, M of P minus 3. Which one am I taking away at each step? Now instead of scraping off the top of the bin, I'm going to cut the weakest link off the bottom of the chain, right? Whichever predictor has the lowest correlate capacity from a predictive standpoint is going to be the first one removed. So I choose to cut off the features that provide me with the least additional capacity to predict the system. What's going to happen in each case? The curse of dimensionality is going to get less and less profound. Every single time I remove a feature, I'm reducing a full dimensionality from the spatial construct that I must search through. You reduce a dimensionality, it is reducing an exponential search characteristic. So you're reducing the complexity of the system by an exponent every single time you're removing a feature. It's really cool because by the time you get to the end of a few features remaining, likely you're going to end up with something along the same lines that forward and backward selection are going to have approximately the same relationship at the end. However, it's not guaranteed because removing the worst ones versus including the best ones up to a certain criteria is not always guaranteed to stop at the same point. Okay, so backwards and forward selection are often used kind of in conjunction with one another or to kind of get a mid-set point, and they're utilized with cross-validation methodologies to make sure that what the the particular points you're selecting from are broad enough for the full extent of the feature space. So we use the k-fold of k minus 1 folds, right? To do the training or to do the selection for the feature subset selection. And then we use the internal subset test selection to determine whether or not, based upon the criteria given, adjusted R squared and RSS, whether or not we selected the best subset for that. We're going to then average the performance across all k folds to determine whether or not the subset that we selected is representative across the entirety of the population. Because it is possible that for the small amount of features that you have contained within your data set, you will not have a full representation of all possible configurations of those features, and thus would choose to remove one that's actually maybe a bit stronger in the general populace than it is in the subset that you selected. So that's why, that's actually, in my opinion, the reason why this is a more full justification of the reason why K-fold is good for both N and P for subset selections of sample subset selections and feature subset selections, right? We typically just use the term subset selection for features, right? And then we use folding selection for samples, N. Those are the most common terminologies. All right, we're going to talk about, we'll continue to talk about operations and estimations, and then we'll talk about these techniques, CP, KIC, and BIC criterion, as well as the adjustment to R squared that we're going to employ in order to solve the problem of including too much of the label information within the characterization of which features are best to include in the subset. We want to try to balance out the amount of information that we're giving the selection process so that we don't bake in too much of our labeling into our data set selection. Because if we do that process, we can bias it towards already sort of knowing that because these features were selected, that it's likely that this is the best value in the set, right? It's weird that it can do that. It can intuit certain things based upon the marginals of certain features being present in that space, right? So we have to avoid it. We have to, as I said, line tamer. Get out our chair and our whip, and we keep that model in line. So we're going to utilize these criteria, calculate these criteria, and then we'll talk about shrinkage methodologies, hop back to the bootstrap, and then hop forward again to the end of 6, where we'll talk about the dimensionality reduction methodologies. Okay? Looking forward to seeing you guys on Wednesday. Hopefully you have a good week.
Sweet.
Okay.
Thank you.
I actually went ahead and posted the rest of the slides for 486 for you.
Thank you.
So I just posted all of the rest of the slides.
That actually.
Except for one, and I'm keeping that one for a surprise.
That, well, I don't go and like try to study them ahead. I just like to have them on my tablet, so I'm prepared to annotate.
You're fine. I realized that, and I thought that today. I was like, I should have just released all of them. So while I had it open, I just did it. So.
We can get it from the website.
You could, and that's the reason why I say you did get it from the website already, so it's like, what's the difference? I think next time I'll just post all the modules in advance and let people choose what they're gonna do. So, usually,